Okay, so here's I.C.E. charts, equilibrium calculations using the I.C.E. chart method. This is video number 2 here. What we've done is we've started our I.C.E. chart. We've created a chemical equation, we've balanced it, we've gone through the first couple steps, which are right here. Okay, we're using concentrations in our chart, and right now we're on step number 3. We're filling in the I.C.E. chart. Okay, so balanced equation, change to concentrations, create the chart, fill it in. That's where we're at. All right, so down here we said that 1 mole in a 0.5 liter container is 2 moles per liter. So we have 2 moles per liter of each hydrogen and iodine. And because that's all we start off with, the initial, remember I is initial, the initial concentration of 2HI is 0, because there's nothing there. Okay, so don't leave it blank, put a 0 there. Now, the change, okay, not that hard, but you need to pay attention here. When H2 and I2 react, what's going to happen to those concentrations? They're going to what? They're going to drop, thank you. They're going to change, they're going to go down. Why? Because they're reacting with each other. So the concentration is going to go down, and this one is going to go down. Now, we'll just, by how much, we'll talk about in a second. So what does that mean about HI? The concentration was 0, and this is going to go, the concentration is going to increase. It's going to go up. So this is going to change in a positive direction, right? Okay, so that's the first step. That's pretty easy. These are going to react right here, and so the 2 moles is going to go down. Now, by how much, we don't know. So this is where we introduce a variable, okay? It's going to go, if this goes down by some unknown amount, this is going to go down by how much compared to X? Yes, the same. Look at it, it's a 1-to-1 ratio. So whatever little change H2 goes down, I2 is going to go down exactly the same because it's a 1-to-1 ratio, right? So you have minus X, and you have minus X here as well. Now what's HI going to do? It's going to go up by, 2X. Does that make sense? So in here, I'll just make a little note here, okay? Use molar ratios, okay? For these numbers right here. 1, 1, 2. Okay, they come from 1, 1, 2. So once again, we start off with 2 moles each, and as they react, they're going to react at a 1-to-1 ratio with each other. This is like the stoichiometry we did last year, right? 1-to-1 ratio. So they're both going to go down at the same rate. So we're going to change by minus X, minus X. This one, for every 1 mole of I2, let's say, there are 2 moles created. So this goes down by X, this goes up 2X. Got it? Now, that's usually the trickiest part there. I mean, and that's not even that hard, is it? You guys can do that. So equilibrium, now we write an expression for what the concentrations would be at equilibrium. Remember, we don't know how much it's changed yet. For this question right here, this type of question, we don't know how much it's changed, but we know that we started at 2 and it's gone down by X amount. See that? So we write the equilibrium concentration expression. So this is also 2, and how did it change? It went down by X. And this one was 0, and it went up by 2X, which means this is 2X. You don't have to put 0 plus 2X. Alright? Now this chart, the reason why we do this chart is to get this, for this type of question. We start off with reactants only, and now we've got an expression as to what it should look like at equilibrium. Is everyone with me so far? Okay. Now how do we find out what the equilibrium concentrations are? Well, we have to solve for X. So that means we need to make an equation. So step number 4 is write the equilibrium constant equation, the KEQ equation. So number 4 is write the KEQ equation. Alright. So, now if we remember how to do this, KEQ equals, it's going to be some ratio, right? And if you remember from the last lesson, It's going to be the concentration of the products, which is HI here, right? And then what do I use for an exponent? Do I have an exponent here? 2. Remember, the coefficient in the balanced equation is the exponent. So the products, now there's only one product, so that's all we use there. Okay? A little bit. And what goes down underneath? Well, the concentration of H2 to the power of just 1, so just leave it like that, times the concentration of I.C.E. Okay? Does everyone see how that is the KEQ expression for that? Okay, remember that? Alright. Now, the KEQ is given in the question. It's 50. Okay, so let's substitute 50 over here for the KEQ. And this is, of course, at equilibrium, and so all of these need to be at equilibrium, and so that's where this comes in. These values get substituted in to the expression. So 50 equals 2x all squared divided by 2 minus x, that's the expression for H2, times 2 minus x, the expression for I2 from the chart. Following me? Okay, good so far? Alright, so chart, we want to get the equilibrium expressions. Once we got that, get the equilibrium equation. Once we got that, substitute all the values in. Now we're going to solve for x. So this is where it's going to take a little bit of math. Not a lot of high-level math here. Some questions get a bit tricky, but watch how this works. This is pretty straightforward. You might see this already. Some of you math, geniuses. But down the bottom here, we really have 2 minus x squared, just like we have 2x squared up top. So another way you could write this, right, is all of this, 2x over 2 minus x squared. Right? So how do I get rid of the squared? I take the square root. So we're going to take the square root of both sides. And why do we want to do that? Because we want to try and get x, we want to try and get x all by itself. So we've got to kind of peel away the layers. And here, both the top and the bottom are all squared, so let's do that first. So what's 50 squared? I'm sorry, square root of 50. You guys all have your calculators handy? You might want to, if you do, you can get it out here. Let's do the square root of 50, and yes, you don't have to, write it in radical form. You can just use decimals. Okay? You know what? For chemistry, no, just do it in decimal form. Okay? Don't take the time to simplify it and write it as an exact value. I wouldn't. Okay? Just plug in your calculator, because when we're talking about amounts of substances, we're really interested in the decimals. If we're in calculus or something like that, then exact values are really important, but not so much here. So it's okay just to do 7.0716, and keep that number on your calculator, because we'll probably need to use that in a bit. But what that means now is we have 2x over 2 minus x. And we'll just use the positive version here, of course, because that technically, mathematically, would be plus or minus, but we'll just do that. Okay? So this is looking like a little bit more like a pretty straightforward equation that you get, in elementary school, probably. So we multiply both sides by 2 minus x. And this math now should be pretty straightforward for you. We want to expand, gather all like terms, and solve for x. Okay, so I'm just going to expand that out here. Okay, so once we expand all this out and we get an x value here, gather the like terms, divide, get x all by itself, we get 1.559. Now, don't just circle that and move on. We have to figure out what was x, right? What did we let x equal? So we've got to go back to the question and figure out what we're going to do next. Excuse me. If the question asks us for the concentrations of all substances at equilibrium, what we need to do is we need to insert our x values into these expressions. Okay? So concentration of H2 at equilibrium is going to be 2 minus 1.559. 0.440962, right? All the numbers in the chart are represented by moles per liter, right? Concentrations. So that's going to be moles per liter. It's going to be the exact same for I2. This is the same expression. Yeah, probably significant figures we're going to want to take a look at eventually here. But HI, right, concentration of HI, that's going to be 2 times X, right? Back to our chart, 2 times X. So that is 3.118074 molar. And if we look back to the original question, I don't think I had intended really to sig figs to be an issue, but you'll see in your questions there'll be sig figs, there'll be precision for each one. So you might see this is 0.500 liters. Okay, KEQ 50.0, something like that. So when you use these values, you can use your significant figures. But for now, I'm not going to mark you on significant figures. If you can get, these values to having at least 3 significant figures here is generally pretty good. So that's what I'm looking for. Those are your concentrations now at equilibrium. Any questions? Oh yeah, the steps. Let's go back to the steps. That's right. Here we may have, that's right. We didn't keep up with the steps while we're doing it, that's right. So let's see what we did. Wrote the K equation. Okay, fill in equilibrium expressions into the chart. From the chart into the KEQ equation. Okay, so we did that. We took the expressions from the third row and we put them into the KEQ equation. So we wrote the KEQ equation, put them in. Then step 6 was solving for the variable. So you have an expression with a variable. Solve for the variable. You may need to do just what we did, take the square root of both sides. You may get a trinomial, like a quadratic looking expression, something x squared minus something x plus something, whatever. You can use the quadratic formula. X equals negative b plus or minus root b squared minus 4ac all over 2a. That one. And then simply just solve for x. So the last couple points that I put on here, test solutions for reasonableness, like that word, just to make sure that your numbers make sense. For example, you may get, when you do the math, you may get 2 values, especially when you're using the quadratic formula, right? You may get x equals 0.1 and 2.1, let's say. If that's the case, and you're saying to yourself, well, which one is right? If you got 2 answers and one of the answers was greater than the concentration you started with, and you have to subtract that, and you're going to end up with a negative concentration, that's the one you reject, right? You don't use that one. So just check that it's reasonable. If you say, I ended up with less than what I started with, well, you can't go into the negative concentrations, right? All right, so that's number 7. Test your solutions or just check, okay? And of course, what I just mentioned, the value can't be greater than the initial values in the chart. And then finally, of course, what we did was substitute the solution for your variable in the equilibrium row of the chart, and then state concentrations as your final answer. So those are your kind of 8 steps. If you kind of get lost and where are we, okay, where am I, what do I have to do next, these steps will help. I will just go over this last paragraph here with you. When you do your assignment, okay, a lot of the questions will be like this one that we just did. But there will be some questions where I will be asking you not for equilibrium concentrations, but I may ask you for initial concentrations. So I may give you the equilibrium concentrations, and you might have to work backwards. You can still use the chart. That's what's nice about the chart. You would just fill in the equilibrium row with numbers, and then work backwards, the change back to initial. Okay? So you can use the chart in different ways. And just as I mentioned here, when equilibrium concentrations are given, you're asked to find the original concentrations. In each case, the rows in the chart mean the same thing. You just may have to work backwards. That's why I like the chart, because it's very visual, and you just fill in the spots. It seems to make sense to me. So over the years, this is, the students have found this helpful. Okay? So that's the conclusion of that. We'll do some more examples, but that's basically your instructional video on doing the I.C.E. charts, initial, change, and equilibrium chart. Okay, so here's a sample problem that we're doing. It's on your assignment. Here's the equation. Make sure you know, or you take a quick note as to which ones are in the gaseous state, because those are the ones that are going to go in the I.C.E. chart. If anything is liquid or solid, it doesn't go in there. It's just the gas that we're dealing with here. Okay. What's the KEQ? The KEQ here is 2.00 times 10 to the negative 2. Okay. So this is at 450.0 degrees Celsius. So that's the KEQ we're going to end up dealing with. All right. So we have a balanced equation. Let's make the I.C.E. chart. And yes, this is very similar to the one we just did, right? So this shouldn't be a real shocker. But it's written the other way around, isn't it? So it's written where the products are H2 and I2 and not the reactants like the last one. Notice that the KEQ was large in the last one and it's small now. This means that which are favored? What's favored if you have a small KEQ? Reactants are favored. So at equilibrium we're going to have more HI, right? Okay? All right. So 2HI is here. H2, I2. Now the question says we're going to place 0.120 mole of HI in a 500 milliliter flask at 450 degrees and allow the reaction to reach equilibrium. Calculate the moles of I2 present if temperature remains unchanged. Okay, so what we want is the moles of I2. That's what we're looking for. Not concentrations of everything, just moles of I2. So just keep in mind what we're actually looking for. We're going to use the chart, and then we're going to come back to this. All right, so one of the first steps is make sure that we have concentrations, right? You can't put in 0.12 moles here. You can't do it. You got to do molar, which is 0.120 moles per. We have to write this in liters. So what's 500 milliliters? 0.500 liters. Very good. Because this is, you have to change it because this is milliliters, and molar concentration is moles per liter, not per milliliter. So you get a completely different number if you use 500 as if you use 0.5. Okay, so if you divide something by 0.5, it's the same as multiplying by 2. So we have 0.240 molar. Make sense? Everybody good with that? So where does that go? Can we put this in the chart now? That goes right here. Because initially, I have 0.240 moles per liter of HI. Got it? Make sense? Don't worry about this 2 yet. Okay? Don't worry about that yet. Don't multiply this by 2 because you see a 2 there. No. Just take the concentration, just straight concentration right here. So in the question it says all you start with is HI, and you just allow it to decompose, basically. So what are my initial concentrations for H2 and I2? Nothing, right? 0. So let's put zeros there. All right, everybody got that first row figured out? You okay with all that? Initially, what do we have? Put it in the chart. Okay. Now, change. All right. What's going to happen to the I2 if we allow this to react or to decompose? Because that's what's happening, right? It's decomposing into hydrogen and iodine. So is the concentration going to change? Is it going to go up? Is it going to increase? Or is it going to decrease? It's going to decrease, right? It's allowing to react. It's going to decrease. So it's going to go down. You know that both H2 and I2 are going to increase. So getting those signs straight, first of all, is a good first step. Now, remember, this point is where we use the molar ratios, right? You don't have to write that in each time, but this is just only the second time through with you, so I wanted to put this down here because this is now when the 2, 1, 1 become important. For every 2 moles of HI that decomposes, 1 mole of H2 and I2 are produced. Okay? So, if we were looking at that, we could just put X here. But then, if we dropped by X, this would have to be up by 0.5X. So what I'm suggesting is this. You know that this is going to drop, and the ratio says 2 to 1 to 1. So you know what? Let's just put those molar ratios right there. For every 2 times a certain amount that HI decreases by, H2 and I2 are going to increase by half that, which is X. So we don't have to deal with any decimals here. Okay? So down by 2 moles is the ratio up by 1, up by 1. Does that make sense? So you pretty much just look at the ratio and you just use those coefficients, and then that's, for most of these questions, that's going to be right. Everyone understands that? Good? All right. So 0.240 minus 2x is going to be our expression at equilibrium here. This is going to be x. This is going to be x. Okay. The next is the KEQ expression. So if we take a look at this KEQ expression, what's it going to be? Well, product's always on top, right? So H2 times I2. And use the square brackets, remember, because that means concentration. Don't use the parentheses. Divided by HI concentration squared. Use the coefficients as the exponents. Alright, so we're at that point now, and to fill in the expression, we use these equilibrium values, and where is it? Here, this KEQ value. And we just put that in and go from there. We solve for x. So this is going to be 2.00 times 10 to the negative 2 equals, so we've got x times x on top, and we've got 0.240 minus 2x on the bottom. Yes, squared, because it's squared here, yeah. Alright, so you can just write this as 0.02 if you want now, 0, and that's going to equal x squared over 0.240 minus 2x all squared. And we can do the same thing that we did with the last example and just take the square root of both sides to get rid of these squares here, right? So we take the square root of both sides, and then we're going to multiply both sides by the denominator here. So that basically goes up there. I'll just show all my steps for you. Expand to get rid of these brackets so that we can combine all the like terms. Okay. Now we add add this to both sides. So we get 0.033941 equals 1.28284 x, because remember this is a 1, so you're adding 0.21. Divide by 1.28284. And then we should get an x value down there. Here now, after that math of 0.0264578. And again, we don't just circle that and move on. We have to go back and see what was that x representing. Okay, it was representing the concentration of I2 and H2. The question says, what are the moles of H2? Okay, so the concentration of, I2. The concentration of I2, we know is 0.0264578 moles per liter. Moles per 1 liter. And how many liters do we have? Okay, it's a 500 milliliter flask. So again, this is all gas. So if we have that many moles per every 1 liter, how many moles do we have in half a liter? That should be obvious, but if it's not, right, you can just go ahead and do this. Don't feel bad. That's moles per 1 liter. How many moles in the 0.5 liters that we actually have there, right? And so you're just multiplying this by 0.5 or dividing by 2. So again, if we have 0.02 moles in 1 liter, if you have half a liter, you have half as many moles. So the moles of I2 would be, and we have 3 significant figures given in these problems, so if we go to 3 significant figures, that would be great. 0.026, 5 divided by 2 equals, you don't have to write that step, 0.0132. Okay? So there's your moles of I2. Okay, so that's another ICE chart question there. If you have any questions,